simple harmonic motion, some energy considerations. We know that the time dependence of the position x of t is given by a cosine omega t plus phi 0. If we choose for simplicity the initial conditions such that as t equal to 0, x is equal to a, this expression will become x of t is equal to a cosine of omega t. Let's work with this just for simplicity, so we don't have to write the phi 0 factor every time. We also saw that if we take the derivative of this, we end up with negative omega a sine omega t. And if we take another derivative, we get the acceleration negative omega squared a cosine of omega t. We also saw that the period is 2 pi over omega, with omega squared being k over m, which means the period is 2 pi square root of m over k. Remember the scenario: we have a spring and we have an object attached to it, and the object is allowed to oscillate along the x-axis without friction. The original position of the object with the spring relaxed is 0, and the object oscillates between a and minus a as given by this expression. Cosine of omega t goes between 1 and minus 1, so the object oscillates between plus a and minus a. I draw here the position of the object, a random position of the object at some time t. At this position, the object is moving, whether to the left or to the right. Therefore, it has kinetic energy, so the object is moving. Therefore, it has kinetic energy. At the same time, the spring is deformed, whether stretched or compressed, which means it has potential energy, elastic. So let's work with these two terms. The kinetic energy is 1/2 mv squared, or 1/2 m v squared omega a sine of omega t squared. So the kinetic energy is 1/2 m omega squared a squared sine squared of omega t. Similarly, the potential energy is 1/2 kx squared, which means 1/2 k x is a cosine of omega t squared, or 1/2 k a squared cosine squared omega t. These are the expressions for the kinetic energy and for the potential energy. We saw already that omega squared is equal to k over m, which means either of these two terms can be rewritten. For example, we can rewrite m omega squared as k. So when we add the kinetic energy and the potential energy, this being the total energy of the object spring system, which means kinetic plus potential elastic. This becomes 1/2 Ka squared sine squared omega t plus cosine squared omega t, which is obviously equal to 1. So the total energy will be 1/2 Ka squared. Not surprisingly, this is the potential energy. 1/2 Ka squared is the potential energy when x is equal to A, or plus minus A for that matter. And we are not surprised, because at that time the kinetic energy is 0. By the same token, the total energy can be written as the kinetic energy when the potential energy is 0, and that is when x is equal to 0. It is when the object is passing through the equilibrium position. So in that case, the total energy will be the maximum kinetic energy which is equal to 1/2 m v max squared. But v max is equal to omega A. So this becomes 1/2 m omega A squared, or 1/2 m omega squared A squared. But m omega squared is equal to k, so 1/2 Ka squared. The same result that we found before. So we can write the total energy is either 1/2 Ka squared or 1/2 m v max squared, or 1/2 kx squared plus 1/2 mv squared. The first term is when x is equal to A, plus minus A. The second term is when x is equal to 0. And the third term is for any random x.